Okay, so looking at this problem here, so I've got two particles, P and Q, masses 5 kilograms and 3 kilograms respectively, connected by light and extensible string. Particle P is pulled by a horizontal force of magnitude 40 newtons along a rough horizontal plane. This implies there's going to be some friction involved. The friction is 0.6 G on the 3 kilogram mass and 1 G on the 5 kilogram mass. Okay, so we're going to start as ever by getting our diagram right. So let's make it nice and neat and tidy. Okay, so I've got my horizontal table or road or whatever it is. I've got these two particles that are joined by a light and extensible string. I'll call them, well, they're called P and Q. P is 5 kilograms, Q is 3 kilograms. Okay, so this implies there is a force acting down on each one. So on P it's 5G, on Q it's 3G. Right, so particle P is pulled by a horizontal force of 40 newtons, so actually it's going to be going this way here. So there's my 40 Newton force, and that is sort of towing Q. Okay, so let's finish off with some more forces. I've got a frictional force of 0.6 G on the 3 kilogram mass on P. 1 G on the 5 kilogram mass, so it's 1 G going that way, and 0.6 G on the 3 kilogram mass. Don't forget that friction opposes motion, so by common sense this system is moving to the left, so the friction must be opposing the motion, so that's going to the right. Okay, so I'm going to add two more forces on, because bear in mind that if this was just like this, P would be moving downwards because there's only a 5G force, so there must be a reaction force, normal reaction on P. I'll call that RP, and I will call that one RQ. I know that my acceleration is going to be in that direction. I think that's common sense again. And then one more force I have, so I have this tension opposing the motion of P, so it's acting against P. So I suppose it's, think of Q is kind of dragging P as P is moving along, so this tension in the string is caused by Q. And because the string is light and extensible, there is equal tension here. So this is the force that is pulling Q to the left. So that is a full set of forces on that system. So we can now start resolving. So first of all, find the normal reaction and the acceleration of each particle. So let's do the normal reactions first. So if I resolve up on P, the normal reaction RP is equal to 5G. Okay, so RP equals 5G. Simple as that. If I do the same thing at Q, I've got RQ is equal to 3G. So those are the two normal reactions. All right. Okay, so let's now think about the acceleration. Okay, so there's three things we can do on a system like this. We can either resolve for P, or I can resolve for Q on its own, or I can resolve for the whole system. Okay, so I'm trying to find A, so I think in this situation the appropriate thing to do would be to resolve for the whole system. Okay, and I'm going to go this way because that is the direction of the acceleration, and I'm going to apply Newton's second law. So I'm saying what I'm doing it on, which direction I'm going, and what I'm doing. Okay, so those are the kind of three things we need to state when we're resolving. So I need to find the resultant force for the whole system. So what do I have going to the left? So I have 40 newtons. I have this minus t, and I have a minus t here and a plus t here, so they cancel each other out. I don't need those. I've got a minus 1g going in this direction, and I have a minus 0.6g going in that direction. The weight of the whole system is 8 because it's 5 plus 3 kilograms, and A. So A is equal to 40 minus 1.6 times 9.8 over 8. So that is what I'm going to put into the calculator. Oops, sorry. So I've got 3.04 meters per second squared. Okay, so the next thing I'm going to do is I'm going to find the tension in the string. Right, so remember what I said, I can either resolve here, here or here. So I've done the whole system, so I'm going to do I'm going to resolve either P or Q. So I will resolve at P, and I'm going to go in that direction because that's the direction of the acceleration, and I'm going to do F equals ma. Okay, so my resultant force is 40 minus G, the 1G, minus T equals the mass, which is now 5. Don't forget, I'm only thinking about just this part of the system. None of this matters anymore. All I'm interested in is the forces acting on P itself. So these are the only ones I've got, those three. So the mass is 5, and I know acceleration is 3.04, which is what I've worked out there. So that should be T equals 40 minus G minus 5 times 3.04. So I can put all that into the calculator all at one go. So I've got 40 minus 9.8, should have written really, minus 5 times 3.04. So I've got my tension equals 15 newtons. Okay. Finally, I've got this sort of, I suppose it's maybe a little common sense type question really, to explain how the modelling assumptions that the string is light and extensible have been used. So the fact that it's light means that the fact that it's inextensible means that these two tensions are equal. It also means that if you think about, if this string had some elasticity in it, then these two items might be going at slightly different accelerations. So it's almost common sense, isn't it? If this was an elastic string and this moved forward, this wouldn't just follow it, it might slow down and then sort of spring forward. So that inextensibility and that lightness means that we can assume the tensions are the same in the string and the acceleration is the same for both particles. So we can state that the tension and acceleration are equal for both particles. Okay, so that would be the solution to that question.